All right, here's the continuation of evaluating the definite integral as a limit of the Riemann sum for infinitely many rectangles for the function f of x equals x minus 2. We're evaluating the integral x equals 0 to 4 of f of x dx equals the limit as the number of rectangles n goes to infinity of the sum I equal 1 to n of f of x sub I times delta x using the right endpoints. All right, let us proceed. We're up to the point where we say this is equal to the limit. We pulled this value inside and we simplified. We got 16 over n squared times the sum of I times I over I times I minus 4n times the sum over I of 2. And we're able to do this using the summation rule number 2 from note 109. Okay, now look at this. The sum over I of I will use rule 4, and the sum over I of a constant 2 will use rule number 1. Both of those are found in note 109. So the limit as n goes to infinity of 16 over n squared times n plus 1 over 2. Wait a minute, where did that come from? That came from note number 109, rule number 4. Okay, let's continue. Minus 4 over n times 2. Wait a minute, what did that n times 2 come from? That came from note number 109, rule number 1. Go back and look at it. Now we're just simplifying by canceling common factors on the top and the bottom. That gives us a limit as the number of n rectangles goes to infinity of 8n plus 8 over n minus 8. Okay, simplify further. We'll break up 8n over n plus 8 over n and then bring down the minus 8. We'll cancel the n's. We get the limit as n goes to infinity of 8 over n. Well, what happens as n goes to infinity? The denominator grows infinitely large. The entire number goes to 0. This 0 is an accurate answer for the integral, which is an accurate representation of the area under the curve f of x. And we'll demonstrate that with sketches. Thus, we've seen in the videos that we saw 3 videos. We've seen the Riemann sum, a really rough estimation. R sub 6 equals the sum of 6 rectangles, I equal 1 to 6. The function evaluated at x sub I, that's the length, times the width, delta x. And let's do the graph. Here's a graph of our f of x. That was f of x equals x minus 2. And we're going from x equals 0 to x equals 4. And here is our right estimation, our right endpoint estimation, which was actually too big. We did the estimation where we took the positive values, those are the values of the areas above the x-axis, and we subtracted the negative areas, those are the areas under the x-axis. And it still gave us a number that was just too large, 4/3 too large. But the second estimation we did, that one was right on. That was using the definite integral as the limit of the Riemann sum, not for 6 rectangles, but for infinitely many tiny little rectangles under the curve. When you have infinitely many, you get an accurate description of the area under the curve. And when I say under the curve, of course, there's positive area and negative area, so under and over the axis. So here we have the same sketch that we had before for the function f of x equals x minus 2. We have our endpoints, but we have our negative area and our positive area. And a is equal to a positive minus a negative. And that actually turned out to be what we got right above here. We got the area equal to 0 exactly. Now, I'm not concerned about it being equal to 0. It can be equal to any number you want. The point is that is an accurate answer of the representation of this area. You know, looking at that right picture gives me an idea. How about we just evaluate the integral this way? What if we just use the area of the triangles in the picture on the right? I wonder if that would work. Let's just give that a try and see if that'll work. A equals 1/2 base times height. Well, the first triangle was in the picture on the right, we call that a sub minus. It had base equal to 2 and height equal to 2. So the area of the a sub minus is equal to 1/2 the base times the height, which turns out to be 2 units. And then the other triangle on the right side, the part that was a positive part, a plus, that area had a base of 2 and a height of 2, so the area of that a plus is 1/2 times 2 is 2. Thus the area equals the positive area minus the negative area gives me 2 minus 2. Yeah, it gives me 0. So you know what that means? If you have something that's very easy to calculate the area of, you can actually just look at the area of each of the pieces, calculate them with formulas you already know, add, subtract them together, and get your answer, unless you're asked to do a limit. If you're asked to use the area to estimate, just the area of the figures in the picture, then you could certainly do something like we did here on the very bottom of this note, number 109C.